Ladies and gentlemen, welcome to Global Math Mentor. And this video is all about the solution for the CIE Further Mathematics Paper 2-2 for the May-June 2025 series. Paper 1-2 is already solved on my channel, and I will share the link in the description. Make sure you watch that one too. 2 hours exam, 75 marks. Before we begin, you can pause the video and quietly go over these instructions carefully. Let's begin with question 1. Find the roots of the equation. It's a z cube equals to 27 minus 27 iota. It's a complex number giving your answer in the form re iota theta, which is the exponential or Euler form of the complex number. R is positive and theta is within negative pi and pi. So keep an eye on that as well. So in order to find the 3 roots, because it's going to be cube root of this complex number, first it's better to express it in Euler form. This is right now in Cartesian form. So what do? R is the modulus of the complex number, which is 27 squared plus a negative 27 squared, and root that. So I can use a calculator for that. 27 squared, the negative doesn't matter, and square root answer. Let's keep it exact, 27 root 2. It doesn't say exact, but it looks nice. I usually try to give my answers as exact as possible. Okay, how do you find the argument? You make the Argand diagram real and imaginary x's, and you go to the 4th quadrant. Since this is a 27, the real part is positive and the imaginary part is negative. And we know that this angle is just going to be a pi over 4. So the arctan of 1, or the tan inverse of 1, is a 45-degree or a pi over 4 in radians. But this is going to be a negative pi over 4 since it's a clockwise angle in the 4th quadrant. You can also think like, is it allowed to go anti-clockwise? I mean, the answer is technically correct, but that exceeds my angular domain. So we have to keep the negative pi over 4 as our answer. So z cube can now be written as r e iota and theta, which is a negative pi over a 4, right? So now we cube root it, 27 root 2, e to the power let's write it like iota, a negative pi over 4, and plus 2k pi. Remember, these are circular functions. So I can put a 1/3 over here. Now we assign some values, integer values for k, and see which one falls within the given domain. So k, let k be 0. That can be one possible cube root. So the 27's cube root is going to be 3. And what about this thing? It's going to be half times 1/6. So can I say the 6th root of 2, right? Let's keep it exact. And e to the power iota, this is going to be just a negative pi over a 12, right? So k is 0. So pi over 4 times 1 over 3. I'm using the index rule. Powers multiply with each other. So this is one possible answer. So I can think of, let's say, 1 and see if it fits within that. 3 and the 6th root of 2, and e to the power, what will this be? If I put a 1, this is going to be 2 pi 8 minus 1. So that's a 7 pi over a 12. And you can either write iota here or there, it doesn't matter. And that is very much in my angular domain, right? So that doesn't exceed pi. Let's box this one as well. And if I take k to be 2, let me just check. So 4 times 4 is a 16, minus 1 is a 15. Oh, that will exceed. So I'll have to take, I guess I need to go with -1 this time, right? Because the other one exceeds. So 3, the 6th root of 2, e to the power. So if I put a -1, it's going to be a -8 and a -9 pi over a 12 iota, which can be simplified to 3 6 root of 2 e to the power of negative 3 pi over a 4 iota. And these are my answers for the first question. Question 2. Let I sub n. This is an integral 0 to 1 minus x to the power of n sine hyperbolic x dx, where n is a non-negative integer. Part A, show that for n more than or equal to 2. This is a reduction formula that we need to prove, right? Okay, so let's go. I sub n, we use integration by parts, which is going to be 1 minus xn to the power of n, and sine hyperbolic x, if you integrate, you get a cosine hyperbolic x, and 0 to 1 limits, minus the derivative of this first expression, n1 minus x, n minus 1, and times a negative 1, right? And integral of sine, which is going to be cosine hyperbolic x and dx. Let's put in the limits. So if you put 1, that's going to be 0, minus 0 will give you cosine hyperbolic 0. So cos hyperbolic x is e to the power x plus e to the power minus x divided 2. So if you sub in 0, you get a 1, right? Okay, so that's going to be 1 minus, or you can say plus n times 0 to 1 minus x to the power n minus 1 cosine hyperbolic x dx. And I can call this bit as e because it's a repeated by parts case. I need to go once again with this one, n minus 1 cosine hyperbolic x dx and 0 to 1. This will look like 1 minus x to the power of n minus 1, a sine hyperbolic x. Cos integral is a sine hyperbolic, right? And 0 to 1, minus 0 to 1. And now this will be n minus 1, 1 minus x to the power n minus 1, and times a negative 1. And the integral of cos hyperbolic x is going to be a sine hyperbolic x dx. Let's simplify this. If you apply a 1, that's a 0, and sine hyperbolic x is written as e to the power x minus e to the power minus x divided 2. So if you sub in 0, that's going to be a 0. 1 minus 1. Okay, so that's a 0 plus n minus 1 times. Now look at the rest of the integral. That is just exactly same as the question given. The only thing different is, oh, that's going to be n minus 2. This will be I sub n minus 2, and that's a n minus 1. So let's sub this in E, sub in E, the first one. So I sub n is going to be minus 1 plus n times n minus 1, and this whole thing like a I sub n minus 2. And this is the required result. So if you have any doubts, confusions, you can always comment. There are some different ways in which you might have seen a different way of doing integration by parts. This one is a classical method for integration by parts, but I'm talking about that one when you suppose U, a TV, a V, and a TU. So if you have any confusions, maybe I can post a separate video on types of integration. So let me know about that. So now we use the integration formula to get the next bit, find the exact value of I sub 2. So I sub 2 is going to be minus 1 plus 2 times a 1 and I sub 0, which is like a minus 1 plus 2 I sub 0. So what's I sub 0? That's going to be 0 to 1. 1 minus x to the power n just goes away. That's a 1. So all I'm left with is sine hyperbolic x and dx. That's going to be cosine hyperbolic x and a 0 to 1, which is going to be cosine hyperbolic 1 minus a 1, right? So let's sub it there to cosine hyperbolic 1 and minus a 1 and This is going to be another -1. Let's write it this way, right? Okay, so 2 cosine hyperbolic 1, a -2, and that's going to be a -3. So that looks quite exact, or maybe you can write E1 plus E minus 1 over 2 and a -3. So these cancel. So E plus E to the power -1 and -3. Yeah, that's better. So they said that they need I sub 2 in exact form. And that is question 2. Question 3. By considering the binomial expansion of z minus 1 over z to the power of 5, where z is cosine theta plus iota sine theta, use de Moivre's theorem to show that cosecant 5 theta is this thing, and where a, b, and c are integers to be determined. So it's a de Moivre's application question. Let's begin with this. So z is given as cosine theta plus iota sine theta. 1 over z can be written as z to the power -1. So if I apply the de Moivre's law, that's going to look like to the power of -1. So that becomes the coefficient of the angle, but we know that since cosine of a negative theta is just a cos theta, but sine of negative theta is a sine theta. So remember, sine is an odd function and cos is an even function. So this becomes a cos theta minus iota sine theta. So if I look at this z minus 1 over z to the power of 5, that's going to be written as, so I just need to subtract these two. So cos goes away, and you'll be left with 2i sine theta raised to power 5. So iota square is a -1. So iota raised to power 4 is a +1. This will look like 32 I and sine raised to the power 5 theta. I know I can trick this into making cosecant to the power of 5. So let's keep it this way right now. Now I need to expand this. So I can use the binomial theorem, or maybe I can quickly use Pascal triangle like 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and 1, 5, 10, 10, 5, 1. You can use combinations, but that I find that easier. So z minus 1 over z to the power of 5 can be written as z to the power of 5 plus 5 is z4 and a -1 over z plus a 10 z cube, a -1 over z squared plus a 10 z squared, a -1 over z to the power of 3, and plus 5z, a -1 over z to the power of 4, and finally plus a -1 over z to the power of 5. Sorry about that. You will not be writing here. Do not write in this margin. It's written over there. So this will be now z5 plus z, that's -5z cubed. That's going to be a plus 10z. I'm using indices. That's going to be -10 over a z. And or I can maybe write it z to the power -1. You get it. I'm going to be using the de Moivre's law, so let's write it that way. So that's going to be plus 5 over z cube, or z to the power -3, and minus z to the power of -5. So we know that the left-hand side of this expansion is just a 32 iota sine to the power of 5 theta. And now the right-hand side can be written as, this will be a cos 5 theta plus iota sine 5 theta. So you get it, like I've got the value of z, so I'm applying the de Moivre's law. And -5, this is going to be cosine 3 theta plus iota sine a 3 theta. So I can get into the next line, plus 10. That's going to be cos theta plus iota sine theta. And this will be a -10 cos theta minus iota sine theta. Oh boy, another line, plus It's going to be 5 cos 3 theta minus iota sine 3 theta. So, and finally, this is going to be minus cos 5 theta and minus iota sine 5 theta. Okay, now I need to carefully look at some of the terms which I think can be canceled. This cancels this one. And I have this one and this one. All the cost terms cancel. So I can keep an eye on the proof that you're trying to get. So you can see all the sign terms are there. So definitely the cost terms will cancel each other out. And now every term has iota, so we can get rid of iota, sine 5 theta. Let's just write it like this first. So this is going to be a 2i sine 5 theta. A minus 5 and minus 5 is going to be negative 10 iota sine 3 theta. And what about these? This will be plus 20 sine iota sine theta. So we know we can get rid of all the i's. So sine 5 theta will now be written as like a 1 over 16 iota sine 5. Let's forget the iota sine 5 theta minus, this is going to be 5 over 16, right? Sine 3 theta and plus 1 over 16. Oh, that's not a 1. That's going to be a 210 and 216. Let's keep it this way because I need the single denominator anyway. Sine theta. So I can get rid of the 1 over 16. Let's simplify. This is going to be sine 5 theta minus this 5 sine 3 theta and plus 10 sine theta. That's a sine 5 theta. Do I have more? Oh, I have more space. That's wonderful. So cosecant 5 theta, this is going to be the reciprocal of this, which is a 16 divide a sine 5 theta minus a 5 sine 3 theta and plus 10 sine theta. And let me just take a look at it. And where A, B, C are integers to be determined, and that should be the required answer, right? Question 4. The diagram shows the curve with the equation. So the equation of the curve is y equals to 1 over a root x, e to the power root x, and x is more than equal to 1. Together with the set of n minus 1 rectangles of unit width, part A, by considering the sum of the areas of these rectangles, show that this result. Okay, so now we need to consider each one has a base of 1 and the height. So we need to calculate the areas, right? So this area is just going to be base times height, which is this height is going to be, so I can just put 1 and then 2 and so on. So I know that this will look like 1 over a root 1 e to the power root 1 plus 1 over a root 2 e to the power root 2 plus 1 over a root 3 e to the power root 3 plus dot dot dot. And now this is the tricky part, which I think students get confused with. Since I'm taking this side, like the ordinate 1, 2, 3, and so on. So this one is the last one which I'll be taking, which is like a 1 over a root n minus 1 and e to the power root of n minus 1. And we can see that the rectangles are below the curve. So this is an underestimate. So this will be less than the actual area, which is 1 to n and the integral of this thing 1 over root x e to the power root x and dx, right? So you can rewind and check that again. Why did I consider it this way? So they're saying by considering the sum of the areas of these rectangles, show that this thing. So if you take a look at this thing, it's going to be the sum r equals to 1 to n minus 1 and 1 over a root r and e to the power root r. And you can check that actual result shows like the upper limit of the summation is n. This is not n, this is n minus 1. So I'll be adding the nth rectangle in the end. Okay. So before that, I can integrate this thing maybe, and then we can check what goes on with that. So how do you integrate this bit? So let's take a look at, okay, I'm just going to integrate it here so you can take a look at this. So let's say, let root x equals to u, then 1 over a root 1 over 2 root x this is going to be a du over a dx. So dx over a root x is going to be 2 du. I'm using substitution integration to integrate this thing. And when x is a 1, u is going to be a 1. And when x is going to be n, so u is going to be a root n. So let's integrate it now. So again, I need some space. Let's integrate. So area like a 0 to 1 using integration, which will now be, 1 to n instead. This 1 to root n, this is going to look like e to the power u and 2 du. So du stays here and 2 goes out. So this will be 2 eu. Put the limits of integration 1 to root n. And this will be 2 e root n minus e, right? So that's going to be a 2e root n. I'm sorry, my solution is all over the place. Sorry about that. So you can pause the video and just take a look at this. So I'm integrating this thing over here, right? This is my substitution process, and that's my area, right? Okay, so now I can write this thing like a 2e to the power root n and minus 2e. Well, clearly you can see that this doesn't match the result which is given over there. So now, in order to make it like from 1 to n, I need the nth rectangle as well. And what will be the nth rectangle? That's just gonna be like, we can check that. Yeah, that's gonna be 1 over root n and e to the power root n. Let's add that. So 2e root n minus 2e plus 1 over a root n and e to the power root n. Let me just write over here. This is the nth rectangle, right? Okay, so if I factor out 2 plus 1 over a root n and e to the power root n and minus 2e. And that is what I was required to prove, that this sum of the rectangles is below that. It's like an underestimate, right? So let's write shown. All right. I hope that makes sense. And again, guys, if you have any problem, make sure you comment and I'll definitely get back to you as soon as read your comment, right? Okay, so is there more to this? Oh, use a similar method to find in terms of a lower bound for this. So what is this idea of lower bound? So once you have the upper bound, then you go for the lower bound. And for that, you need to consider, look at this diagram. Now we'll consider like, what if the rectangles are above this curve, and that will give you the lower bound, right? So for that, we need like these as the heights of the rectangles, like the upper ordinates, like from 2 onwards to the end. So let's go. If I again use a similar method, so 1 over root 2 e to the power root 2 plus 1 over root 3 e to the power root 3 plus 1 over root 4 e to the power root 4 plus dot dot dot, and plus this is going to be 1 over root n this time, since I am using the upper ordinate. And this is going to be definitely more than the integral 0 to 1 over a root x and e to the power root x dx, right? Okay, so I can write this thing, but again, I need now, since it doesn't fill all of the thing, I need the first one as well. And this is going to be limit, like you can see the summation that starts from 1 for, but right now this is starting from 2 to n, 1 over root r and e to the power root r, which is greater than And this, by the way, I have it right with me, which what was the actual integral which I calculated earlier, which is going to be 2 e to the power root n minus 2e, right? So that is it, right? Is that it? Yeah, yeah, that's it. So I hope you get the idea. I don't have, if I wish to bring that first thing, like from 1 to n, 1 over root r e to the power root r, then that means that I need to add the first area, which is just going to be 1 over a root 1 and e to the power root 1. That being added, my final answer is going to be, so the lower bound is going to be root n. This is just e, so minus a. And that should be the answer for the second part. Question 5. Find the particular solution of the differential equation. The boundary conditions are given. It's a second order differential equation. And for this kind of an equation, we construct the auxiliary equation first. And it's a homogeneous equation. Take any arbitrary constant, let's say k. For the double derivative, k squared plus 3k and plus 6 equals 0. If I divide it by 3, it's going to be 2k squared plus k and plus 2 equals 0. Let's solve this thing, and it's going to be minus 1 plus minus b squared minus 4ac. 1 minus 16, that's going to be negative 15, okay, over a 2a, which is going to be 4, and we have imaginary roots for the aux equation, 15i over a 4. In this case, the complementary function is written as x equals to e to the power of negative 1 over 4 t, because x is in terms of t, and I write cosine a root 15 over a 4 t plus a sine root 15 over 4 t. And don't forget, there are some arbitrary constants over here, which definitely we need to evaluate in this thing. So if you want like a deeper analysis, how we construct these auxiliary equations, complementary functions, in particular integrals, like the detailed idea behind it, I'll definitely make a separate video on that, and you can comment on this video that you need a separate video on that. But right now, I'm just solving it. And by the way, in your exam, you are required to remember like when the roots are real, what kind of a solution the complementary function gives, and so on, right? Okay, so this is the one with the imaginary roots. And now we go for the particular integral. How do we go do that? Like, look at the right-hand side of the equation. It's e to the power negative t. So I'm going to make x equals to any arbitrary constant again. So let's say a e to the power negative t. That's the particular integral. And now I need the first derivative, which is going to be minus a e to the power minus t, and the double derivative, which is going to be a e to the power negative t. So now we multiply this and see what do we get. So that's going to look like 6 sub n a e minus t, because the double derivative's value, by the way, sorry, that's equivalent to d squared x over dt squared, and this is equivalent to dx over dt. I hope you get it. I just use the prime notation over here. Okay, so that's it. And now I need to put a plus 3, and oh, that's going to be a negative 3a e to the power negative t, and plus 6a e to the power negative t, and the right-hand side is e to the power negative t. So none of the e minus t is 0, because we know that exponentials are positive, so you're left with 6a minus 3a plus 6a equals to 1, and that's going to be 9a equals to 1. This implies that a is going to be 1 over a 9. So my particular integral can now be written as 1 over 9 e to the power negative t. Now the final solution of the differential equations are the complementary function plus the particular integral. So now we add both of them, which is going to be e minus 1 over 4 t, a cosine a root 15 over a 4t plus a b sine root 15 over a 4 t and plus 1 over a 9 e to the power negative t. Okay, so now we use the boundary conditions, which are when t is 0, x is 0, and dx over dt is 0 as well. So now we need to differentiate this expression as well. Oh, thank goodness we have more space. So when we sub in the first condition, so 0 will be equal to e to the power 0, which is, can I keep it 1? Yeah, that's fine, 1. And this will be a, since cos 0 is a 1, and sine 0 is a 0, so this becomes a 0, and plus 1 over a 9. This implies 0 equals to a plus a 1 over 9. Okay, so a is going to be negative 1 over a 9. So I cannot use any other condition. I need to differentiate it. So let's differentiate it. So e to the power negative 1 over 4t and times the negative 1 over 4. That's the derivative of the first one. And this a cos root 15 over a 4t plus b sine root 15 over a 4t. So I'm using product rule. I differentiated the first one, second one as it is, plus this time the first one as it is, and the derivative of this thing. So this is going to be a negative a root 15 over 4 sine root 15 over a 4t. So I hope you know the cos derivative is a minus sign, and the angle's derivative is being multiplied as well. Plus, this is going to be b, a root 15 over a 4, and cos root 15 over a 4t. And what about the derivative of this last thing? That's going to be a negative 1 over 9 e to the power negative t, right? So I hope you can pause the video and just try to cope with it. I think I did it all right, product rule and then the separate things. So now we know that this is 0, and again t is 0, so that's going to be minus 1 over 4. You got to be careful while you sub in the limits. It's going to be a plus 0 plus, this is going to be just 1. Let's put it in bracket as well. This is going to be a 0 plus a root 15 over a 4b, because since cos 0 is a 1, and minus a 1 over 9, put it equal to, yeah, that is 0, right? Okay, so a is a 1 over 9. So minus 1 over 4 times a is a negative 1 over 9, my bad. Okay, so plus root 15 over a 4b and minus 1 over 9, put it equal to 0. So now it's going to be root 15 over a 4b equals to a 1 over 9. So plus 1 over 36 minus 1 over 36. So, I mean, you can use calculator for this one. 1 over 9 minus a 1 over 36. That's a 1 over a 12. Okay. So for thrice, so b will now look like 1 over a 3 root 15. So you can keep it like that. That's fine. I was thinking about rationalizing this expression, but that's okay. So now I can finally write my solution as, so a, which is a minus 1 over a 9. Oh, wait, there was a e to the power minus 1 over 4t outside as well. A, which is a minus 1 over 9, cos root 15 over 4t. Right, that is okay. And b is, that's a plus 1 over 3 root 15 sine root 15 over a 4t. And finally, plus 1 over a 9 e to the power minus t. I mean, if you want to, it's not a compulsory step, but you can factor out as well. Minus 1 over 3 cos root 15 over a 4. Not a necessary one. You can do without that as well. Sine root 15 over a 4t and plus 1 over 9 e to the power minus t. And that is the final solution for this differential equation. Question 6, part A. Starting from the definitions of tan hyperbolic and secant hyperbolic in terms of exponentials, prove that this identity. So you should be familiar with sine hyperbolic x. I'm just writing them once again. Ex minus e to the power minus x divided 2. And cos hyperbolic x is e to the power x plus e to the power minus x divided 2. So since tan hyperbolic x is a fraction sine divide cos, so this should look like e to the power x minus e to the power minus x divided by e to the power x plus e to the power negative x. So the 2 cancels with 2. So this is a crucial point you should know. Exponential definitions of hyperbolic functions. So let's pick the left-hand side. And that should look like 1 minus tan hyperbolic squared u. That should be 1 minus e to the power u minus e to the power negative u and divided by e to the power u plus e to the power minus u and squared. So if I try to write this as a single fraction, this should look like e to the power u plus e to the power minus u squared minus e to the power u minus e to the power minus u squared, and divide the whole thing by e to the power u plus e to the power minus u whole squared. Okay, so what about the right-hand side? I think it's better if I simplify this a bit. E2u plus e minus 2u and plus, well, that's just going to be a 2. Minus, this is going to be e2u minus e to the power minus 2u. And this will be now, since it's negative, so negative negative becomes a positive 2. And divide the whole thing by e to the power u plus e to the power minus u. You can try this. I'm using expansion identity for the binomial. So my final answer should look like 4 divide e to the power u and e to the power minus u whole squared. So let's pick the right-hand side. So I need the secant hyperbolic squared u. That should look like the reciprocal of cosine hyperbolic. So that will be 2 over. Oh, so this, sorry, my bad. That should be u plus e to the power minus u and whole square this. And this will end up 4 over the same thing that I just proved with tan hyperbolic. So hence proved left-hand side is equal to the right-hand side. Let's take a look at this part B. Okay. So I need to differentiate secant hyperbolic inverse t. I mean, there can be a direct approach to such a question, but let's take a look at this way of working this out. If I say let y be a secant hyperbolic inverse t. Now look at this. T will end up secant hyperbolic y, right? So, I mean, secant hyperbolic y, now this becomes an implicit function, and I can differentiate it with respect to t. But if you want to figure out like what's the derivative of a secant hyperbolic, I can just give you a slight idea on that. So d by dy, d over dy of secant hyperbolic y can be written as like a derivative of a 1 over cos hyperbolic y. So this will be second as it is derivative of first minus first as it is, which is a 1. And cos, this will be a sine hyperbolic y. Divide the whole thing with a cos hyperbolic y squared. So this will be a negative secant hyperbolic y and tan hyperbolic y. So this is a good way, like you can just dive in and see, like if you do not find the direct way of integrating, or you haven't memorized the formula, you can always design it, right? Okay, so now we differentiate this whole thing with respect to t. And this will be, the left-hand side will be 1. This is going to be, now we just figured it out, minus secant hyperbolic y, tan hyperbolic y, and dy over dt, right? So dy over dt will end up a negative 1 over a secant hyperbolic y. And now I can express this, just take a look at the identity we proved earlier. So secant square hyperbolic y is 1 minus tan squared, right? So tan squared is going to be 1 minus a secant square hyperbolic y. So this will be 1 minus secant hyperbolic squared y. So I just use the A parts identity. You can check that. The reason is I'm keeping an eye on the proof I'm trying to prove. So we know that secant hyperbolic y is a t. So hence, d over dt of a secant hyperbolic inverse t will end up a minus 1 over a t times the square root 1 minus t squared. Again, I'm just saying this is one way of differentiating it. There can be more ways, but you can learn this implicit way of differentiating these arc functions and hyperbolic functions, which are inverse hyperbolic functions, by the way, right? So that's all good. And now we can move to the next one. Oh, there's a big one. It is given that x is a tan hyperbolic inverse t and y is a t secant hyperbolic inverse t. Show that this. So if you're familiar with your normal A-level math course, these are known as parametric equations. So x is in terms of t, y is in terms of t. Let's differentiate them separately. Dx over dt is going to be, we have a direct derivative in your MF19 formula booklet. You can check that out. That's going to be 1 over tan hyperbolic inverse x. Derivative is 1 over 1 minus x squared. So this way I can just write it 1 over 1 minus t squared, right? That's the straightaway. And now I differentiate the dy over dt. That's going to be a 1 and a secant hyperbolic inverse t plus t. And secant hyperbolic inverse, we just found it out. What was the result? It was going to be a t over. So you see, it's a connected question. They made us find this derivative first in terms of t, so we can use that. So now I apply the chain rule. So dy over dx is going to be dy over dt divide the dx over dt, right? So this will be okay, so I can do a secant hyperbolic inverse t minus a t over square root. Oh, these t's will cancel, right? Wait. So these t's will cancel. And I can just write minus 1 over square root 1 minus t squared. Okay. And I multiply because the denominator becomes the reciprocal. So this will be just a 1 minus t squared. Let's time this. And that will look like, okay, I can write it the other way around as 1 minus t squared, a secant hyperbolic inverse t, and minus 1.5. If you use indices, this will end up a half power in the numerator. And that is exactly the same thing. Okay, I can write it the other way around. So hence, this is shown, right? Secant hyperbolic inverse t. I use the product rule for differentiation, and first I use the parametric chain rule thing, and then some product rule, and this is a hyperbolic differentiation. But obviously, the fundamental concepts are the same: product rule, quotient rule, chain rule, power rule. That's the same thing, right? Oh, now I need to double differentiate this thing, right? So how do we double differentiate? D squared y over dx squared. This is implicit double derivative. So this will look like d by dt of a dy over dx. That's the key idea, divided by dx over dt, right? So I'm again using the same philosophy chain rule. So let's differentiate the dy over dx first, right? Okay, do I have a lot of space? Let's begin. So this is going to look like a minus, okay, let's just write it 1 over 2, a 1 minus t squared, a negative 1/2, and times a negative 2t, right? Plus, this is going to be a minus 2t and secant hyperbolic inverse t as it is. Oh boy, I'm out of space. Can I fit it here? Okay, like 1 minus t squared, I'm sorry. If you find it jumbled, you can just pause the video and see. This as it is, and secant hyperbolic inverse t, we already have the derivative, so that's going to be just a minus 1 over t times a root of 1 minus t squared. So I'm sorry about that. That is just the numerator and divided by 1 over 1 minus t squared, since we have the dx over dt right here. We found it. It's a connected question again. And that's the implicit double derivative. Let's cancel this out and see what do we get out of it. That's going to be a t over a square root 1 minus t squared. And I can put the 1 minus t squared right here in the top, right? This denominator. And sorry about that. Okay. So now, what happens when I simplify it further? Minus 2t, a secant hyperbolic inverse t, and this will be a minus just a square root of 1 minus t squared and divide by t, right? Okay, let's simplify this further and see what do we get. So this will be t times a square root of 1 minus t squared. That's the d squared y over dx squared. And minus 2t and 1 minus t squared times secant hyperbolic inverse t, and minus 1 minus t squared and raised to the power 3 over 2 and divide by t. Well, that should be my final answer. Question 7. Find the solution of the differential equation, this, given that y is 0 when x is 0, and give your answer in an exact form. If you observe this, this is an exact differential equation. It's of the form this plus p of x of y equals to q x. So we know that p of x will be a negative x plus 5 over, I mean, you can put that in a bracket, x squared plus 10x plus 61. And qx, on the other hand, is just going to be 1. So in these kind of differential equations, the integrating factor is found. And how do we get this? It's going to be e to the power integral of this p of x and dx, right? So how do we integrate this? Let's try and integrate this expression. So negative goes out, x plus 5 over x squared plus 10x plus 61. Now that is a type which is taught in A-level pure mathematics 3 as well, and in further math. So you time and divide with the 2, the reason being the derivative of this thing is in the numerator. So this kind of an integration is simply minus 1 over 2 natural log of x squared plus 10x plus 61. So when you raise it to the power of e, we can simplify it this way. When you raise it to the power of e, x squared plus 10x plus 61, so this negative half goes to the power. So negative half power can be written as this thing. This looks better. And that is another simplification. E to the power ln any function is just that function as well. So what I'm trying to say is e to the power natural log of any function is just f of x. The reverse log rule, 1 over x squared plus 10x and plus 61 and square root that. So that is my integrating factor. Now we multiply the integrating factor with the given differential equation. So that will look like 1 over square root of x squared plus 10x plus 61 times dy over dx and minus, now you got to be careful here. It's going to be x plus 5 over 1 plus half. That's going to be a 3 over 2 and y as it. And since qx is just a 1, the right-hand side will look like x squared plus 10x plus 61. Sorry about that. That is my calculation with the integrating factor. Now, this is the interesting part. Now, this will look like the derivative of a y times the square root, 1 over square root of 10x plus 6, x squared plus 10x plus 61. Well, you can check that. That's the interesting part about these exact differential equations. They end up, so if you see one of the function is 1 over square root of x squared plus 10x plus 61, the other one is y, and it's just simply a product rule, which is going on up there. So the right-hand side is still this thing, x squared plus 10x plus 61. So now we integrate this again. So integrating to solve this differential equation. So y over a square root of x squared plus 10x plus 61 will look like the integral of this thing. Well, in order to integrate this thing, I think it's better if we express it as a perfect square minus plus 61. That's going to be x plus 5 squared. And let me just check. 61 minus the 25. That's going to be 36 plus 36. Oh, that's an interesting form. So you can write it like 6 squared plus x plus 5 squared. And if you know the type, the hyperbolic integration, this is going to be sine hyperbolic inverse of x plus 5 over a 6 and plus c. Don't forget that, y over a square root x squared plus 10x plus 61. So that's it. And now we need to evaluate the constant. So y is 0 when x is 3. Oh, thank goodness I have more space. X is 3. So this is going to be 0, and this is going to be sine hyperbolic inverse 8 divides 6 plus c. So c is going to be a negative sine hyperbolic inverse of 4 over 3, right? And that's it. Y is just going to be the square root of x squared plus 10x plus 61 and times this whole thing like a sine hyperbolic inverse x plus 5 over 6. I'm keeping my answers exact. Reason being that the question says that you need to give your answer in exact forms. And that should be my final solution. Question 8, part A. It is given that lambda is an eigenvalue of the non-singular square matrix A with the corresponding eigenvector E. So according to the given statement in part A, this means that A times a vector E is going to be lambda times E, where lambda is the eigenvalue, E is the eigenvector, and A is the non-singular matrix. Show that E is an eigenvector of A cube with the corresponding eigenvalue, lambda cube. So we wish to show, let's consider like this should look like a cube E. And I wish to prove that this should end up a lambda cube E, since they want us to show that E is an eigenvector for both matrix A cube with the corresponding eigenvalue of lambda cube. So let's split it like A squared times AE. And this will be A squared times a lambda E according to the given result. And lambda is just a scalar, so you can pull out the scalar, factor it out, and A squared E. Again, you can use the same idea, lambda times A and times AE. So this will be lambda A and a lambda E. Lambda is a scalar. You can pull out the scalar, AE, and that is going to be lambda squared times a lambda E, which will be lambda cube E. Hence, you can say that A cube E equals to lambda cube E, proved. So you just proved the statement that E is indeed an eigenvector for the matrix A cube with the corresponding value, eigenvalue of lambda cube. All right, so next part. They're saying the matrix A is given by this. Part B, show that the eigenvalues of A are these values. There's a 2-mark question, so we need to set this singular matrix A minus lambda I, its determinant equal to 0. So, 2 marks, I'm just going to use a shortcut. So you can maybe try and simplify, pause the video and see that this will end up a determinant like this. 1 minus lambda, 0, 0 minus 2, and a 5 minus lambda. Put it equal to 0. So minus 1 minus lambda. And this is going to look like 1 minus lambda and times a 5 minus a lambda and minus a 0, right? Subtract, this is going to look like 3 and, oh, that's simple, 0 minus 0 for this entry and plus 4. That is going to be, again, a 0 minus 0. That's why I think they just gave 2 marks for this kind of a result. Now, all I'm left with is this product If you put it equal to 0, so lambda turns out to be a -1, lambda turns out to be a 1, and lambda turns out to be a 5, right? And that's proved. You can say shown. Okay, so next bit, they're saying part C, find the matrix P and a diagonal matrix D such that A minus 2I is a PDP inverse. It's a diagonalization question. P, we know, is a matrix whose columns are eigenvectors, and D is the diagonal matrix whose diagonal entries are the eigenvalues, and rest of the members are just 0 since it's a diagonal matrix. So, but we need the corresponding eigenvalues for this matrix A minus 2I. So if you know this result, that will be beneficial. This will be like if I have the eigenvalues of -1, 1, and 5 for A, this implies that the eigenvalues of A minus 2I will be -3, -1, and a 3. So I just subtracted 2 from each of them. Quite fundamental. We don't have much space. So now what do we do? How do we find the corresponding eigenvectors? Oh, I'll be needing my matrix A. Let me just write it because I'll be needing it again and again. -1, 0, 0, 3, 1, and a -2, 4, 0, and a 5. Right? Okay, so let's begin. So you can say when lambda is a -3, then I need to set A minus 2I matrix and minus a lambda I, so lambda is -3, it's going to be +3I, and times that vector x and equals to 0. So this means that A plus I need to evaluate this. This is going to be a 0, 3, 4, 0, and a 2, 0, and 0 minus 2. And this is going to be a 6. So I'm doing it in my head, but I'm just keeping an eye on A and adding the identity matrix. So what does this mean that times the vector x, y, z is a 0? This means that each entry into this vector is a 0. So this vector has to be perpendicular with each of these row vectors. So let's set the scalar product, the vector product. And that's going to be any two vectors will do the job. You can take the last one or the second one. It's okay. You'll see it will end up the same. So let me just use a shortcut. 0 minus 8. And that's a 0 and that's a 0. That's good. So I can just simplify it to 1, 0, 0. So this is the eigenvector corresponding to the eigenvalue lambda equals to -3. So I'm just trying to compress my work. We don't have much space. Let's go. When lambda is a -1, this means that A minus 2I and plus I times the vector is going to be a 0, right? Okay, so this will give me A minus I. So now let's just simplify this matrix. It's going to be -1, -1, that's a -2, 3, and 4, 0, a 0 and 0, that's a 0 vector, so we don't use that one. We don't use origin, so that's going to be 0, -2, and a 4. So times again that x, y, z, that's a 0. I need to set my scalar product. Why am I saying it's scalar product? So vector product, my bad, cross product. So that's going to be take any two and that will do the work. So for this one, don't use the 0, 0, 0, but the rest. So this is going to be 12 plus 8, 20. -8, that's going to be a +8 and a 4. So if I simplify this, it's going to be 5, 2, and 1. The eigenvector corresponding to the eigenvalue lambda equals to -1. When lambda equals to 3, again, I would use A minus 2I and -3I. So that's just going to be A minus a 5I. Let's get this matrix. It's going to be -6. Yeah, 3 and 4. And then I will have a 0. 1 minus 5 is a -4. A 0. 0 minus 2. And a 5 minus 5 is a 0 as well. So you know what to do. Set the vector product, the cross product. Any two vectors will do. 0, -4, 0. And let's say 0. I can use -6, 3, 4. So this is going to be a 16 for the -16 for the first one. And have I used the incorrect order? Oh, I think I need to set it like a -6, 3, and 4, and any two. Like, well, let's use the last one. I just wanted you to know, like, oh, that's going to be +8. That would have done as well. Like, you can maybe take out common in the end. And this is going to be -12. That's just a 0 and a +12. So this is going to be 2, 0, and 3. Right. So that's it. P is going to look like 1, 0, 0, 5, 2, 1, and a 2, 0, 3. And the diagonal matrix is going to be a -3, -1, 3, and a 0, 0, 0, 0, 0, 0. Okay. Oh boy, that was a big one, and with a little space. Let's go for the next one, part D. Use the characteristic equation of A to show this result, A minus 2I cubed equals to this thing. Okay, so I need the characteristic equation, and then I'll be using the Cayley-Hamilton result. Make sure you look into that, how the eigenvalues result can be transformed to the matrix. So if they encourage me to use the characteristic equation of A, I can write lambda plus 1, a lambda minus 1, and a lambda minus 5. So let's simplify this. It's going to be lambda squared minus 1, lambda minus 5. This will be lambda cubed minus 5 lambda squared minus lambda and plus 5 equals to 0. So if I convert this, this is going to look like a cubed minus 5a squared minus a, and plus this is the part you need to know, that this is going to be 5i. So let's see, now I expand a minus 2i cubed. So I can use 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. That's going to be a cubed plus the 3 times a squared minus 2i plus 3. That's going to be a times the minus 2i squared and plus a minus 2i a cube. So that's going to be a cube. I can fit in the a cube that I just figured out. So that's going to be, oh, this implies that a cube's value is going to be 5a squared plus a and minus 5i. So that's going to be 5a squared plus a and a minus 5i. And now we just simplify this. It's going to be negative 6a squared. You know that a squared times I is just a squared, since that's the identity matrix, so you can just ignore that. So that's going to be plus 4 3s are 12a, and again I squared is just I, and I square or I times a is just going to be a. And this, by the way, is going to be minus 8i cube, and that is just I. I cube is just I. So this will give me negative a squared. I need the constants to be determined, and plus the 13a and minus the 13i. And yeah, that looks all right. Okay. And that's it for this exam. And I hope this walkthrough really helped you. You can always rewind, save some chunks out of this video. And again, I would really like to encourage you to please subscribe to the channel. I see my analytics, and a lot of you watch the videos and just leave with no subscription. So that hardly takes any energy. Keep following for more useful resources. This is Global Math Mentor, over and out.